Hi, everybody. My name is Natasha Wilkerson, co-founder of Vivify STEM, and welcome to this session on how to apply science standards in your STEM classroom. So in this session, perhaps you are a science teacher and you want to integrate some more engineering design that fits with your science standards. Or you're a more general STEM teacher or engineering teacher that want to create more meaningful connections to the science content. We're going to tackle all of that in today's session. Welcome. All right, let's get started. So again, this is all about how do we add science in a meaningful way to our STEM challenges. A little background about me. I began my journey in STEM as an aerospace engineer. I went to Texas A&M, graduated in aerospace, and then worked at the Department of Defense for a few years. There's a picture of me as a baby engineer working out in Green Bank, West Virginia. We were actually doing some testing of some satellite dishes and looking at frequencies and how they move through different terrain. But after a few years of that, I got hooked into education. I started volunteering with some kids after school and just loved helping them make those connections and bringing my experiences of engineering into the classroom. I worked as a STEM director for 8 years at a nonprofit where I created a program called Space Club. And this is an elementary and middle school after school program where we integrate engineering design with math and science through space exploration. So you can see us doing a space lander. We do rocket launches. We've launched a weather balloon to the edge of space. It's been a phenomenal program. And with that, I also write curriculum and lead the efforts over at Vivify STEM, along with my partner, Claire Meshkat, who also has another session in this conference. Okay, so let's dive in. Here are some pictures of my Space Club kids. These are all middle school students. And they are doing different types of engineering design challenges or what you might see in a STEM classroom. So you have things like the tower challenge, they're trying to hold up a ping pong ball. You have the drag device challenge where they're trying to keep what I was calling an astronaut in the cup when it was landing. There's a catapult challenge. And my question to you is, where is the science? So if you are a STEM teacher or a science teacher, you may be able to pick out some topics that this could be covering. The tower challenge, we build a tower to hold, a weight. Perhaps they're learning about forces acting on the tower, center of gravity to keep it balanced, the structural properties of different materials. The drag device, drag right there in the name. How does changing the size of the parachute impact how long it takes? So again, forces there with the drag pushing up, gravity pulling down. And then the catapult. Elastic potential energy comes to mind as a way to make it more elastic to make that launch farther. But the question is, when you walk into a classroom and they're doing the drag device, they're doing the catapult, are they learning that science? Is the student holding that catapult who went through days of tinkering and redesigning and building that whole design process, does she better understand elastic potential energy? And that's the topic we're going to tackle today. There was a study that came out a couple years ago, and they observed science lessons that were through engineering design. So they're in a science classroom doing engineering design challenges. And what they found was only 11%. So they looked at hundreds of hours of classes. Only 11% of those design challenges were actually helping kids better understand the science. And you might already have ideas of why that is. Perhaps the teacher wasn't there to really make it explicit. Maybe the kids were learning it in a different part of the unit, and in that design challenge, it just wasn't apparent how it was connecting the design activity. And the problem with this is engineering is now in our science classroom. So if you are an NGSS state, we now have these standards that bring in engineering. If you're in Texas, where I'm in Texas, we now have engineering practices being introduced next year. And our goal in science is to teach science. And the problem is, if we're replacing science content with engineering, we want to make sure that it's actually meeting our goals, our objectives to teach science. And what they're finding is maybe it's not. So I'm going to take a look at this activity. This is one of our activities on brain safety, and we connect it to a football helmet, and the students are tasked with creating this device to protect an egg from cracking in a similar manner that a football helmet protects a football player's brain. So the science topics we could cover are Newton's laws, shock absorption, and then material properties. This is typically how an activity like this would look. So they look at the materials. I have cotton balls, I have cardboard, I have rubber bands, and then they draw a design idea. Well, I think it should go like this. It should stretch like that. Then they pick the materials based on what they already kind of know about them. Well, cotton's really soft, so maybe it'll help cushion the fall. And then they build it and they test it. Did the egg crack? Oh no, it cracked. Dang it, we got to go back and try again. Yes, it didn't crack. Let's celebrate. And often teachers are like, okay, let's go higher. Can you go from 3 feet now, 4 feet? How high can we push your design? And then the reflection is often about the process that happened. So how did testing go? How did you get through those places where you were stuck? So like the perseverance. And often we talk about like habits of mind. Are you communicating with your team? Does your design communicate your ideas? But did they learn the science? Did they make the connections of why certain materials were useful in their design? And the answer for me is no. They did not learn any science in this lesson. They learned how to intuitively use different materials, and then sometimes their intuition was wrong. So they were able to rethink and redesign based on those experiences they had with initial materials they chose. But again, our science content isn't being explicitly taught. Okay, this is a crazy slide, but it does do a good job of explaining these 3 dimensions of science. So if you're in the NGSS land, you will have these 3 dimensions, and now Texas is also based on 3 dimensions of science learning. And the idea is that we have some core ideas. That's the DCIs, disciplinary core ideas, and you can see that with this orange, the rope I'm looking at. It's a collection, and that's also in this Venn diagram, the orange side. It's a collection of science content, like forces in motion, talking about like gravity and why things fall to the earth. And then we have cross-cutting patterns, which are like these bigger ideas like patterns and cause and effect. And then we have science and engineering practices, the doing of the science and the doing of engineering. And these are meant to all come together and help us promote science learning. And so engineering fits in those practices. Engineering through the NGSS is looked at as the application of science. So engineering, you're going to do something to improve your design, to come up with a better solution. And then by that doing, you're improving your understanding of science, because engineers are supposed to apply what they know about science to their design. And the core ideas outlined by the NGSS are define the problem, develop solutions, and optimize. And I really like how it's so simple. I've seen some really crazy design processes, but this is the core idea. What am I trying to do? What's the best solution? How do I make it better? And that's a really great way to approach engineering, especially at the lower grades. Also, these slides are available as a download, and there's a bunch of links in there that you can get. This is like Canva graphic that we created, so you can have this if you want to use it, or you can use these slides for presentation, whatever you would like. Hopefully this is useful. Okay, so let's go a little further. We have science and engineering in NGSS are put together. There was a great paper by Cunningham, who is the founder and creator of EIE. Awesome stuff. And she basically says, let's really be careful when we talk about science versus engineering. So like that first NGSS practice, asking questions and defining problems. Well, in science, the goal is very theoretical. Okay, we want to understand this phenomenon. Engineering, the goal is often a useful, novel technology. So it's creating a thing, a process, a product, something. And I think this is a really nice chart that kind of breaks apart the science versus the engineering. You can see like engaging an argument from evidence. Our goal is to persuade scientists in the community that our ideas, our way of thinking of a phenomenon is the right way. And then we have the evidence to back it up. And then in engineering, it's to satisfy our constraints. So basically considering, okay, I want to design it this way. Here's my argument. And I would also say that this should include justifying your design decisions based on the scientific principles. So I chose the cotton balls because it has these material properties. And we'll get into that in a minute. If you're in Texas, you can compare and contrast here the NGSS science and engineering practices with those in Texas. They are almost identical. So we see asking questions, defining problems, word for word the same. Developing and using models. They're over to the right. Develop and use models. So everything is basically translated into Texas standards. A few things are tweaked a little bit, but NGSS and the framework that created that is really much influencing how Texas does these science and engineering practices. Okay, so the way that the NGSS is, and this is the same in Texas, are wanting to help support teachers in integrating engineering with science. So how do we bring these together? They pull in these standards. So what you'll notice with these standards is they are a science or engineering practice, they're a core idea, and they're one of those cross-cutting concepts. That intertwined rope thing, it's all in one of these standards. So you can see this first one. Analyze data, so you're doing something. Obtain from testing, again, practice you did. Testing different materials to determine which materials have the properties that are best suited for an intended purpose. So again, you're looking at the doing and then understanding this concept of material properties and then applying it to some kind of design solution. And TEACS is almost very similar, kind of worded differently, but demonstrate that materials can be combined based on their physical properties to create or modify objects such as building a tower, and justify the selection of materials based on their physical properties. So the goal and the way they promote integrating science with engineering is you're doing engineering while applying some of the scientific knowledge, but it's just not as simple as that, right? Based on like the earlier slides of, yeah, kids are doing catapults, they're probably, or even the egg challenge, they're thinking about material properties, but are they really understanding the science? Is it really helping them understand material properties or kinetic and potential energy? The other piece here, so this one is these standards here, and that's what's in the chart. There are these core ideas: physical science, life science, earth and space science. They are each, some of those standards have an engineering practice embedded within it. And then there's the last column, which is engineering. I think it's like ETS, engineering and technology, maybe, is more explicit on engineering practices. So the NGSS sees engineering as a set of practices. There are no core ideas in engineering, which is completely false. We'll get to that later. But that's what they want you to focus on, is engineering, the doing of engineering, and then how can we integrate it with how we're teaching science. Okay, so all of that was kind of philosophical and more of the how NGS is doing it. So let's get to the practical. That's why you're here. So how do we actually implement this? How do we implement an engineering design activity that actually teaches science? So I'm going to propose a couple strategies. The first two, you can see here. First one, students first learn the science concepts. So you go through a whole science unit and then apply them to a design challenge. So we build up that knowledge and then kind of test it and really help them deepen that understanding through a design activity. Strategy two is you just throw them in a design. You let them tinker around and then you pause. You reflect on like what worked, what didn't, and then you introduce some information that might be helpful through a science concept and then they use that science concept to then make a modification. So it's like a need to know basis, like, oh, my design isn't working and I'm not quite understanding what's going on. And that is a perfect moment for you to walk in and introduce some science, and that helps them make some really strong connections. So let's talk about some examples. Strategy one is applying what they learned. And the key here is you've got to be explicit, because kids naturally just want to throw stuff together. So if you really want them to learn some science, It is on the teacher to guide them there and really enforce that you want these design concepts to be integrated with a science-based decision. So 2 examples. One is this instrument. So kids can just create musical instruments and say, create an instrument that makes sound. But if we want them to take it a little step further, well, how do we change the frequency of that sound? What did you have to do to your drums or your guitar? You can do like really easy one out of different rubber bands and have different thickness of rubber bands. And then how do you change that amplitude of sound? How do you make it louder? How do you make it quieter? So this idea of designing an instrument using what they're learning about sounds. They would have already learned it, and then they're reinforcing that content. I will say, though, the design of instruments is not quite an engineering expertise. So we call it design, but there's some kind of nuances when we use the word design. So yes, they had to build and then test if it did create different amplitudes and then redesign. But it's not typically an engineer that is designing instrument, but it is an engineer that is designing a heat shield, which is that next example. So it might be a material scientist, aerospace engineer, mechanical engineer that are designing a heat shield to keep astronauts alive. And what they need to know here is this idea of heat transfer. What are my forms of heat transfer and how do I prevent them? And so then they can look at material properties. Well, what material property is important? Conduction, right? And insulation. Well, how do I know if something is a conductor? Well, it's online. We have done the research and we figured out these properties of materials. And so instead of kids just intuitively coming up with what they think would work, we can have them use some data. So you could either go online and figure out how conductive is that spongy material versus the felt versus the paper, or have them do a conduction test where they just take the piece of paper and they put one side on a heat source like a hairdryer, and then they feel the other side and see how long it takes for the heat to transfer. So it's using that data to then inform their design and hopefully reinforcing that science content. Okay, so stage 2 now. This is a little bit of a different approach. So instead of science first, engineering later, we start with the engineering problem as the motivation. Here's the lander, another space for my Space Club program. I tasked the kids with designing a lander to keep 2 astronauts alive when landing on Mars. Real classic design challenge. So they need to design it. They can only build below. It's not a parachute, right? So I just let them go through the whole process. I don't give them any other context. So they're tinkering with materials, playing around. And often what you see on this left side with those reddish lander devices is they really focus on this idea of shock absorption. And how do we have like this shock, kind of thinking of springs, like that's what they're intuitively wanting to do. And then I introduced this idea of drag and center of gravity. It's kind of 2 key ideas, because what I noticed is they're never thinking about increasing the area. And then everything's so wobbly, it's falling off center and falling out. And then what you'll see is like, okay, how do I apply this idea of larger surface area, more drag? And there's some activities you can do to help them understand that, but they're going to see it the most obvious in their design. And all of a sudden you have a team here that expanded the area of their lander. I've had others make a whole fan array of index cards. How can we maximize this area to really capitalize on the science phenomenon of drag? And then you could have them, explicitly talk about forces. So again, it's you as a teacher has to be the one really encouraging that application of science knowledge and helping kids make those connections from the doing of engineering back to the science concept. It's a hard leap for them sometimes because what they're not used to is that science content is actually applicable to their everyday lives and the way they interact with things. And so that's why I love engineering, because it helps them move out of this, like, I'm in school and this is science and I'm memorizing it, okay, whatever, to like, oh, wow, this is real. I can see the heat transfer and how different materials transfer heat differently. And then I can apply it to something really cool. So that's why I think engineering is a cool way to do that. In the science classroom, we often use the 5E learning cycle. You have engage, explore, explain, elaborate, and then evaluate sometimes at the end, but often should be throughout, like as a formative assessment throughout your learning cycle. And then also at the end is like a summative assessment. Let's bring it all together. Do you really understand the key ideas? So kind of pulling from those two strategies, you can integrate engineering throughout. The first one is the engage. And this is where you do an activity that may not be exactly related. The same concepts aren't used in the design, but it helps kids get interested. So what you'll see down here is an oil spill challenge, where the students are told about the scenario of this big oil spill and how it's harming all these creatures. And they need to use their design skills to figure out a way to absorb as much of the oil they can from this water. Later, you're going to go into maybe a discussion about oceans and the different animals in the ocean. And it doesn't necessarily directly connect to what they just did with sponges and cups and different absorption materials. So there's a disconnect in the science, but it's there to just get them excited and motivated for the unit. The other piece is explore. So this is where in the way I use explore in my classroom is I don't introduce any vocabulary. I haven't introduced the science yet. I just want them to experience the phenomenon. So let's say you do this drag device. So now I can build like a parachute. And I have them do the design challenge, but in a more structured way, where I say, let's see which parachute is going to hit the ground first. Do you think it'll be the smaller size parachute or the larger size? What is going on? So they're using this data from this design challenge to start building some intuition, some understanding, looking at patterns in their data that can then be kind of cemented with this explain, elaborate phase of explaining the concepts that they just experienced. So making those connections. And then finally, you could put a design challenge at the end of your unit. Like the other strategy was like, we've just introduced a bunch of science. You feel pretty confident with it. Can you now apply it to your design challenge? And this is where anytime they make a design decision, they need to justify it based on some key ideas and constantly making that connection. Okay, so I'm going to end here with a discussion on what I consider authentic engineering. So again, my background's in aerospace engineering. I'm also a doctoral student at Texas A&M, and I have recently conducted a survey of engineering faculty. So these are people that are engineering professors preparing undergraduates to become future engineers. And I think their opinion is really important because I would like them to tell me, is what we're doing in K-12 preparing our students to become your students? Are they doing things that actually represent engineering in undergrad and then real professional engineering work? And it's not that I care about everyone being an engineer, but if we're going to talk about engineering, I want it to be authentic. I want it to help students be prepared for these engineering pathways, but also just understand what engineering is about, how does it work? And the thing that I've gotten from the survey, most faculty think the way we do in K-12 is actually very flawed and creates some big misconceptions. So here's my egg drop football helmet design. Students use this tinkering approach. They try different materials. They intuitively were like, this is going to work. This isn't. Again, we got the point, like they didn't really understand any of the science. But the other problem is they didn't really understand engineering either. So NGSS breaks it down with like design, develop solutions, optimize. The way real engineering works is through predictive analysis and using some very deep reservoirs of knowledge around how materials work and some of these phenomena that are very important to design work. And that's both on the material side, like understanding these material properties, but also the machining side, like how do you actually make that and put that together? And it's not so much through tinkering. So you can see pictures here of a football helmet undergoing some kind of analysis on a computer. And from the D, it's the thickness represented by different colors. And then they can put a load on it. So they could put that in a simulator and say, okay, if you get hit from this side, what will happen to the materials? What will happen to this side? And that's where, when we say predictive analysis, there's calculations we can do from our understanding of how materials work when you're bent and hit and moved in certain ways. We know how we can predict how they will act. And that's a key piece to engineering. We don't build airplanes by kind of throwing pieces together. We have this kind of big piece of knowledge. Like aerospace engineers know how the air works to lift our airplane. And then they use that to design the materials to be a certain shape. Because we know a pointier airplane will move faster and more efficiently through air. And then the wings need to be shaped in a certain way to kind of increase that lift. And these are pieces that are often missed in these design challenges. And so what I heard from the professors was these freshman students are coming into my engineering class thinking that engineering is all these tinkering activities where we're going to be building bridges and roller coasters out of paper and the catapults from popsicle sticks, when in fact what you do as an engineer is you take a whole bunch of physics, and that's algebra and calculus based physics, and then you take a whole bunch of math classes, and you take a whole bunch of science classes that are very theoretical. So you'll do like thermodynamics, and you'll make a lot of calculations. And it's not until year 3, 4 when design is introduced, because engineers are not ready to design something until they deeply understand the science of how things work, and then how can we manipulate those things, knowing with these like predictive tools. So we have like AutoCAD, SolidWorks, you might be familiar with this stuff, that helps us kind of predict what's going to happen before I actually spend the money to build the thing. And that's often lost in this K-12 space. But it's also really hard to do. So the one way to think about it is ASCE, which is the American Society of Engineering Education, came out with this framework because that was their fear, was K-12 is creating some problems for future engineers, where kids are all of a sudden doing all these really fun activities, but there's just not like a real clear learning goal. When I do a bridge or a tower or a catapult, and often they're repeated over and over and over again. Like how many times have kids done catapults, from kinder through 12th, that everybody's kind of using the same design challenges. And also, what's the difference between the design challenges? Like, what's the point beyond just teaching these optimization? Okay, so I have to find the problem, and then I have the constraints, and then I develop a solution, then optimize. It's kind of like the cyclical thing. And I feel after a few design challenges, kids are like, I got it. But like, what's next? So ASC says, well, what's next and how we should think about this are 3 dimensions. Engineering practices is just one. So they don't think there's anything wrong with the way NGSS is putting in engineering design. Their problem is that there's just a lot more to engineering. And engineering design is just one piece of all of engineering practices. You can see they also have material processing, quantitative analysis, and professionalism, which is more about like how does engineering work, and then how do we work in the workplace. The other piece are the habits of mind, which a lot of teachers do. So like kind of the 4 C's, the 21st century skills. We have collaboration, creativity, persistence. Systems thinking is maybe one that's newer. So how can we understand that our design maybe is just one piece of a larger system? So when we're designing one piece, how does it interact with a whole bunch of other pieces? And then the one that's missing, often in most design challenges, is engineering knowledge. And they break it down as to engineering sciences, engineering mathematics, and engineering technical applications. And for today's talk, I just want to zoom in for a second on that science. So a way to think about engineering sciences are science concepts that are relevant to the engineering world. And it includes both natural and man-made phenomena. Okay, so that's kind of the difference. Questions that those engineering scientists might ask: what slows down heat transfer? So like that heat, the space lander, or the one that I just did with the heat shield. How do I slow down? So we talked about insulators and conductors. And so that overlaps really nicely with what kids are already doing in science. But then other questions they might ask are, how can I make something bouncy? Why does something break? And break is so important. Things breaking is so important in engineering. Finding the failure points, trying to make that connection is so important in engineering. And so this piece is critical. And here's why. To give you another example, this earthquake challenge. This is another activity I've done with students, and we related it back. This is design an earthquake-resistant structure. And we've related it to these standards. This is often how it's aligned. So like in the NGSS, they say, generate and compare multiple solutions to reduce the impacts of natural earth processes on humans. Or middle school one, analyze and interpret data on natural hazards to forecast future catastrophic events and inform the development of technologies to mitigate their effects, right? So we're talking about natural hazards and their impacts to humans. So the way this unit works, first, you learn about earthquakes, right? What is a natural hazard? What is the phenomenon that causes earthquakes to occur? What is going on in the earth? So this is an earth life science, earth and space science kind of category, right? So we see that ES, earth and space science. But then when you switch to the design part, which is coming up with these solutions, none of that science matters. It doesn't matter how an earthquake was formed. That will not help you be a better civil engineer in designing a skyscraper to withstand an earthquake. And that's our split between the traditional sciences of physics and chemistry, earth sciences, like geologists, and engineering sciences. So what you need instead, and what we do in our unit, is we look at material properties. And we talk about, okay, what's the difference between like a thin piece of spaghetti and a really thick piece of spaghetti? What about how we put the spaghetti together and the foundations and different shapes cause us to have more stability? And this is in an area of material properties, statics, which is a college level course and is way beyond the scope of what like a middle school or a fourth grade student can do. So my point here is it's often very difficult to integrate science into a design challenge because the science that we teach in K-12 is not necessarily engineering science. Some of it is heat transfer, great big overlap here. Natural hazards, not as relevant to engineers. What they care about is the structures of how do you withstand breaking down in an earthquake, or if a big wind, high winds are going to come at your building. Civil engineers really care about that. So there's some area of science that is very much within the realm of engineering, and that's where it all gets messy, right? So if you go to a university and you talk to an aerospace engineering professor, they're going to be experts on fluid dynamics, so like how stuff moves through air. They're going to experts on drag, right? These are topics we don't cover very much in K-12. Like fluid dynamics is not something we're really thinking about. We barely talk about drag. Usually we're talking about an ideal world where there is no drag to help kids explain gravity. And we talk about how all objects fall at the same rate because there's no gravity. Like we just kind of push that to the side, which is the part that engineers care about. And that's what they're the experts on. And that's the challenge I see with integrating engineering into K-12 science and trying to get those to talk to each other, is the expertise of an engineer and the science that they use is often very different than that of a traditional like physicist or chemist or biologist. Both are needed, but I hope that this helps kind of gives you a framework to one. Okay, so let me start with this. Here are my takeaways for you. If you want to teach science with your design challenge, your first question should be, what science is relevant here? And for earthquakes, how earthquakes are formed is not relevant to my structure. So am I just motivating the challenge by understanding earthquakes? What are my key learning goals here? And then 2, helping kids understand what is authentic engineering, and that in fact, it's not a scientist discovering something and then handing it off to an engineer and being like, good luck, go build something. It's actually not really how it works. In reality, the engineers are researchers that are trying to understand how say a beam bends, a spaghetti breaks. They're the experts on that. They're the ones studying that phenomenon and then using it to improve their designs. So engineering and science is a fun world. I hope that gives you a little bit of insight on being careful in the ways you integrate science and engineering. And also that I think it's really important, but it's also hard. And also kids may not be ready for a lot of the science that we're trying to put into a design challenge. It's okay. Like, let yourself have the freedom to kind of figure out different design challenges and which work better to teach the science that you want. And it's okay to just do a tower challenge and let them build things and work together and communicate. Those are awesome. I love tower challenges. That's not what I'm trying to say. My point is knowing that's not authentic engineering. That is not how engineers build towers. And also being aware that you're not teaching any science. They're not just going to learn forces in motion. Building a catapult, they're not going to learn elastic potential energy unless you teach it to them, unless you make these experiences meaningful and you ask good questions and you help guide them to that knowledge and really be explicit with, this is the science that we're trying to use here. And look, when you apply it, look how it changes your design and makes it better and responds in the way that you predicted because you knew the science. All right, so these slides are available as a download. There's a bunch of links in there that you can click. I would love to connect with you if you have more questions. This is a kind of topic we cover on the STEM Space podcast if you ever want to listen. And I hope you guys enjoy all the rest of your sessions.